What's up, AP Calculus students? Mr. Ford here with another homework tutorial. This is 5.2.1. We just learned how to do the product rule in, I suspect, a hurry in class today. And so this assignment is meant to last you the weekend. So it's going to be kind of a longer one, but I'm going to record as much as I can. It's currently 9:32, so I got about 23 minutes. We'll see how far we get. All right, 551, we're going to evaluate these integrals without a calculator. So let's go for it. In this first one, we got the integral from 1 to 4 of 3 times u to the 1/2 power plus u to the negative 1/2 power du. And we're going to have to use the reverse power rule and evaluate this without a calculator. So this is going to be, we need u to be to the 3/2 power here. And I need it to be 3 in front. So I'm going to have 6 over 3. I guess 2. 2 would do it there. That would do it, yeah. Because 2 times 2 over 3. Now, am I doing that right here? I need 3 over 2. Usually, let's see. Usually if I want this to just be on its own, I put 2 over 3 here. But I need there to be a 3 in front also. So yes, that would be 6 over 3, which is 2. Yes, I was correct the first time. I should not have doubted myself. Putting a 2 there. If we bring the 3/2 down, it'll cancel out the 2 and leave the 3, which is exactly what we want. For the next term, we need u to the positive 1/2 power, but I need it to cancel out when I bring it down. So I'm going to bring it a 2 in front, plus 2 to the 1/2. Yeah, that works. And we're going to evaluate this from 4 to 1, which is actually kind of nice because 4 and 1 are both perfect squares, which you'll see in a moment. We need 2 times 4 to the 3/2 power, plus 2 times 1, or sorry, plus 2 times 4 to the 1/2 power. Whoops, 4, please. We're going to subtract from that 2 times 1 to the 3/2 power and 2 times 1 to the 1/2 power, which is actually not too hard to do because raising to the 1/2 power is the same as taking the square root. So this is 2 times, get out of here. Let's see, 4 to the 1/2 power is 2, 2 to the 3rd power is 8, and 4 to the 1/2 power is just 2, so 2 times 2 is 4 there. This is just going to be 2 plus 2 inside of this parentheses. So this is going to end up being 16 because 4 minus 4 will cancel out, and so 16 is the final answer. Going to confirm that against my my answer guide here and make sure. Hooray! Question B. Let's see. Question B is probably best done. We have the integral. I'm going to move over. Well, yeah, I guess I'll move all the way over here, won't I? Question B, we have the integral from 0 to 2 of 6 times x minus 4 squared dx. So what we're going to do here first is we're going to expand that out. This is going to be 0 to 2. Well, let's put 6 out in front of the integral, actually. And this is going to be x squared minus 8x plus 16 dx when we expand that. And that's actually pretty easy to do because we'll have 6 times big parentheses. What we're going to have to do is evaluate x to the 3rd over 3 minus 4x squared plus 16x. We're going to evaluate that from 2 to 0. That's actually relatively easy to do because 0, if you plug it in for x, will just cancel everything out. So all we really got to do is plug in 2 there. So this is going to be 6 times, let's see, 2 to the 3rd power is 8 over 3, minus 4 times 4, which is 16, plus 2 times 16, which is 32. And we're going to multiply that all by 6, which is nice because the 8/3 will actually cancel out nicely. This is going to be 6 times 8/3 plus 16. And if we do the distribution now, the 6 over 3 becomes 2. 2 times 8 is 16. This is 16 plus 6 times 16, which is, oh, I'm not using a calculator. 6 times 16 is 60 plus 36, 96. And that's going to end up being 102 plus 10, 112, which is confirmed the correct answer. Hooray! Question C. Question C is actually really stupidly easy because we're taking the integral of a derivative. So all we have to do here is understand that the antiderivative of the derivative of g of x is just g of x, but we have to remember to put a plus c on it because of how we're integrating. Very similar for part D. I don't think there's enough room to do D right there in that space, so I might bring D over to the side a little bit. But D will not take a super amount of space. D is just the integral, let's see, from, it's going to be k to the 8/3 power, and I got to have a 3 over 8 in front of this, so that it cancels out nicely, and we're going to evaluate this from 1 to 0. And again, plugging in 0 won't do anything, so plugging in 1, honestly, the answer is 3/8. Because if you plug in 1, it's 3/8, and if you plug in 0, it's 0, and that's your answer, 3/8 minus 0. So that's the answer to that one. 3/8, or 0.375 if you want to be the book. And then question E is just kind of one more rep of this. I'm going to bring it over here on this side and draw a line. I'm going to first of all rewrite this as the integral from 1 to 2 of 4 times n to the negative third power dn. That'll make the antiderivative relatively easy to get. It's going to be n to the negative second power, and I need this to be negative 2 in front. That way it'll be a 4 when we bring it down. And we're going to evaluate this from 2 to 1. So this will be negative 2 times 2 to the negative second power minus, in parentheses, negative 2 times 1 to the negative second power. So let's see, 2 to the negative second power is, this is negative 2 over 4 minus, that's just 1, so this is minus negative 2. So this ends up being negative 1/2 plus 2, which is 3 over 2, or 1.5, if you like it. There you go. Not too terrible. Okay, next question. We got, this one's top heavy, like they usually are. The next one, we got a bunch of derivatives. Differentiate each function if possible. If the function is not one we can differentiate yet, which is going to happen, say so and explain how you know. So question C is pretty easy to do. I'm just going to write it right down here. Y prime is going to be 100x to the 99th power plus 100. That's the derivative according to the power rule. Question B is also relatively easy because you can just follow the power rule. I might do B off to the side just to get some room here. H of t is t to the negative fourth power minus 6 times t to the 1/2 power. This t to the 1/2 power, we've seen it a bunch, so it's one that's worth just memorizing at this point. You get negative 4 times t to the negative fifth power. I'm going to write that as negative 4 over t to the fifth. That's the same idea. This will be minus 3 times t to the negative 1/2 power. We could clean this up a little bit, I suppose. That would be negative 4 over t to the fifth minus 3 over the square root of t. That's another way to write the same answer. So it's kind of up to you how you want to write it. Question C, we do not know how to take the derivative of 2 to the x power yet. That's not a thing we've dealt with, so this one we cannot do yet. Do not know how to deal with an exponent, a derivative, or a variable up in the exponent. So for questions D, E, for D and E, we're going to need our newfangled product rule for this. So for question D, I'm going to do off to the side. You have x to the 8th, f of x is going to be x to the 8th power. F prime of x is 8x to the 7th. Your g of x, your second function, is the cosine of x, and g prime of x is the negative sine of x. So if we follow the product rule, your y prime is going to be f of x times g prime, so negative 8x to the 8th power times the sine of x, plus f prime times g of x, so 8x to the 7th cosine of x. It's actually relatively simple to figure it all out and put it together. So order doesn't matter. You can put those in whatever order you want. You're just adding and multiplying. For question E, I might do this one off to the side also if I have some room, just because I like to do the prep. I'm running out of space to write on here. Let's see. I might have to fly way off to the side, I guess. For question E, this is question E of the next section, I suppose. I'm going to write it here. The original function, f of x, or on the left, is x to the 5th, and so the derivative of that is 5x to the 4th. I'll zoom way in on this in just a moment. The right function, g of x, is x to the 3rd plus pi, and the derivative of that is 3x squared. I suppose you don't need the product rule for this one. It's actually going to be pretty easy to put together without using it, but I'm going to use it anyway. So the derivative, y prime, is going to be x to the 5th times 3x squared, so that'll be 3x to the 7th power, plus, let's see, we got 5x to the 4th times x to the 3rd plus pi. So if I want to shake all that out, 3x to the 7th plus 5x to the 7th plus 5x to the 4th pi, and those can combine together. That's 10x to the 7th plus 5x to the 4th pi. I think that's correct. Yeah. Oh, the book didn't even simplify it at all. They just left it right here where it was. So, okay. You don't need the product rule for that one because you could just expand. You could distribute. and then take the derivative first. And then f is relatively easy to get right now if you rewrite it a little differently. This is 7x to the negative first minus 1/7 x. So your y prime is going to be negative 7x to the negative second power minus 1/7. That's it. Pretty simple. Okay, let's move on. We got 553. We saw a problem like this in the last homework section. We're going to match up a bunch of f of x's, g of x's, and h of x's to their derivative. First of all, the first three are pretty easy to do without much work. F of x is x to the third. F prime of x is 3x squared. So we know these two go together, a and e. G of x is 6x minus 1. The derivative of that is just 6, so right across the line right there. And h of x is sine of x, and the derivative of that is cosine, so h prime and g go together, c and g. Now where it's going to get hairy is when we start doing composite derivatives. So for example, let's take a look at f prime of g of x. F prime of g of x. We know that f prime of x is 3x squared, so it's going to be 3 times something squared, and g of x is 6x minus 1. So we're doing really composite functions. G of x is 6x minus 1. We're plugging them into the derivative, so we're looking for a, I guess, in that one. For the next one, we're looking for g prime of f of x. Now g prime we found out to be just 6, so hold up a minute. Shouldn't that just be also 6? Yeah, I guess it's also 6. Let's see. Can I confirm that? B goes to B equals? Yeah, they both go to 6. Doesn't matter. G prime is just 6. Doesn't matter what the input function is. It's always 6. That's kind of interesting. Okay, and we got f prime of h of x, which is going to look very similar to our answer. It's 3 times something squared. H of x is the sine of x, so we'll plug that in. That's what h of x is. So we're looking for c right there. And then you got h prime of f of x. And h prime of x is the negative, oh no, just the cosine. It's the cosine of something. And the original f of x was 3x to the third power. So we're looking for cosine of x to the third power, which is option D. And I think there's one, f does not get used. So there you go. Pretty cool. Okay, 554, we got ourselves one of these walking bug problems. We have an ant moving along the edge of the table. Its position from the center of one edge is given by the function, that thing, x of t. When x of t is increasing, the ant is moving forward. What is dx dt right away? Now, you could do this. You don't have to use the product rule for this, but since we learned the product rule today, actually, yes, you do need to, because I do not want to expand t minus 4 to the fourth power. So the best way to handle the product rule is to make a little table like this. I guess it should be f of t. Let me just make sure I get my variables right. F of t is t minus 1. G of t is the other part, t minus 4 to the fourth power. F prime of t is just going to be 1. And g prime of t is going to be 4 times t minus 4 to the third power, according to our power rule. So if we use the product rule, now to put this all together, dx dt, it doesn't really matter what order you do this in. F of t times g prime is going to be a bit of a doozy. It's going to be 4 times t minus 1 times t minus 4 to the third. I'm just grabbing these two things and throwing them together in a multiplication blender. And then that's going to be plus t minus 4 to the fourth, because when we multiply it by 1, nothing really happens to it. So you can see these derivatives are going to start getting more and more complicated as we start doing product rule and especially quotient rule. But so far, that is the correct answer. I'm looking at it in the book, and that is what they've got. X of t represents how many millimeters the ant is from the center of the table after t seconds. What are the units for dx dt? And what information does this derivative give about the ant? So dx dt is the change in position, the change in time. Change in position over time, so that's the velocity. So dx dt, this is the velocity of the ant. And in general, the derivative of your position function always gives you the velocity function. That's the velocity of the ant. And I guess the units would be millimeters per second. Yes, millimeters. Be millimeters per second would be the units. For question C, what are the units for the second derivative? This would be, well, let's see. As far as the units would go, it would be millimeters per second squared, or per second per second. And this is going to give us the acceleration. of the ant. The change of the change, in other words. Does acceleration have 1L or 2? I think it's only 1. Acceleration of the ant in this one. Right there. Question D, how often does the ant stop and change direction, and at what times? Be sure to find and confirm your answer both using calculus techniques and a graph. So we're going to look at the graph in a moment, but I think this one's actually relatively easy to do because we know what the derivative is. So for question D, when we're looking for stop and change direction, what we're looking for is when does this whole thing, 4 times t minus 1 times t minus 4 to the third plus t minus 4 to the fourth, when does this equal 0? In other words, when you want to know when something stops and changes direction, you want to know when its derivative equals 0, just like that. Now, this one looks like it can be really challenging to solve, but it's not that bad if you know one tiny little algebra trick. And that algebra trick is factoring. Both of these two terms involve t minus 4 to the third power. So we factor it out, t minus 4 to the third power. We'll have 4 times t minus 1 plus t minus 4 in there. And now we've turned it into a big multiplication problem. We know, for example, I know that this part of it is true, because these are two things multiplied together, and the answer is 0. So if one of them is 0, the other whole thing is 0. This one happens if t equals 4. It's got multiplicity 3, but that doesn't matter so much. The only real challenging part would be to solve this thing, and that's not really challenging. You just got to kind of pull it off to the side and do a little algebra problem. 4t minus 4 plus t minus 4 equals 0. So this ends up being 5t minus 8 equals 0, and so t is equal to 8/5, or 1.6. Those are the two places where it's going to turn around and change direction. Now, you can tell me that if you're going to go to the graph for a moment, you can see that same information depicted right here. Let's go ahead and graph it. We're going to very, very carefully put our derivative into this graph, and we're going to see when it changes sign. 4 times x minus 1 times x minus 4 to the third power plus x minus 4 to the fourth power. Very carefully making sure the graph looks exactly the way it's got to be. And again, I'm just going to graph this. I know that I'm looking for 1.6 and 4, so I'm going to go from -1 to 6. That'll work. And I really just care about where it's changing direction, so I'll leave my y kind of like that. There's our 1.6 right there, changing direction. And there is also changing direction there. So these are the two places where the velocity of the ant moves from positive to negative and from negative to positive. You can even tell me that this is a maximum speed and this is a minimum speed because of the way the signs are changing there. So you can do that graphically and also with calculus. At time t equals 3, is the ant moving forward or backward? Justify your answer using calculus. Well, we know from the graph that t of 3 is pretty solidly negative. I mean, there it is. There's 3. The graph looks like it's right down about there. Now, we could, with calculus, all we would need to do, I'm going to keep calculator cam in the forefront here, but all you really need to do is check v of 3. This question is asking you, is v of 3 positive or negative? Translation of this problem. If it's positive, your ant is moving to the right. If it's negative, he's moving to the left, forwards and backwards. We know it's negative, so he's got to be moving backwards. Let's just take a look at the table to confirm what v of 3 is. It's -7. So it equals -7, so he's moving backward. If I was taking the AP Calc test and I was going to write a free response question answer, I would say the ant is moving backwards because v of 3 is less than 0. You know the velocity is negative, therefore the ant is moving backwards. Pretty cool. I got about 4 minutes left on this video, so I might try 5:55 and come back and do the rest later. It's going to be probably much later today, I suspect. Probably not going to happen during school at some point. 5:55, we're going to draw a graph of the square root of x times the cosine of x. So the square root of x times the cosine of x. And we are going to graph that from 0 to 3. So once again, bringing the calculator up. Window. Let's go from 0 to 3. Since cosine just oscillates from 0 to 1, I'm going to leave right there. It looks like it's a pretty interesting looking and doesn't really look like it's doing too much. Just doing a thing. The cosine part is oscillating from -1 to 1, but the square root of x is continually growing, so it doesn't really matter too much. As far as an equation for this goes, let's just sketch the graph real quick. 1, 2, and 3. And we have, it looks like that graph doesn't really go above 2 or so on that range. 1, 2. Graph kind of looks like this. As far as the derivative goes, we're going to have to use the product rule again. F of x is the square root of x. F prime of x is 1 over 2 roots of x. That's one you should just memorize. G of x on the right side is the cosine of x, and G prime of x is negative sine of x. So the product rule will say that f prime is going to equal negative square root of x times the sine of x plus the cosine of x over 2 roots of x. If we do the multiplication, there's your multiplication for that one, and square root of x times negative sine of x is right there. We're going to graph that derivative here. The bell, oh no, I'm doing pretty well for time. I was just getting nervous about, no. We're going to graph the derivative. We're going to carefully type it in. Negative square root of x times the sine of x. That's the first term. Plus, I'm going to put a fraction in here. It's the cosine of x over 2 square roots of x, like that. We're going to graph that on the same boundary. You'll notice that it's going to be starting off very steep, but then it's going to slowly level off, which matches what we would expect to happen because the slope of the blue line is leveling off towards 0 very, very quickly. So the derivative graph is just going to come down and approach 0, but never actually touch it, just like that. We're using this graph to locate the x value of the local maximum over 0 to 3. I believe, geesh, I mean, this, I don't see one. Oh. Square root of x times, did I put the original graph in wrong? Square root of x times the cosine of x. I'm not seeing the graph that the book says right there, and I'm pretty sure I'm looking right at the correct thing. I also have the correct derivative, which I am also looking at. Let's see. Am I looking at, is my mode in, oh my gosh. Whoopsie poopsie. Classic calculus mistake. Radians and degrees, my guys. Oh boy. There we go. That makes a little more sense. Like I have all the formulas right. Why is the graph not correct? There we go. So this should match what we see. We're going to see we see the derivative crossing the x-axis right there at that maximum. That's what we're looking for. It's going to do the same thing again, I suspect, over here, probably beyond our window there. So we're looking for where the derivative crosses the x-axis or the maximum of the blue function. They're going to be the same x value. I'm going to use the 0 tool with my derivative. So I need to make sure I push the arrow key down to make sure I'm looking at the derivative function there. I'm just going to go over here, get to the left bound, to the left of it, and to the right of it. There's the bell. And I'm going to push enter there, and it's going to be at about 0.653 or so. So the x value is going to be about 0.653 if I'm rounding correctly. We'll finish this problem up, and I'm going to get my third hour started. Likewise, use a graph of f double prime. You know what? We're going to have to come back to this when I finish this video later on today. So product rule, keep practicing it. It will come with lots of practice. It's actually pretty easy once you get the hang of it. And I will see you in the next video where we'll finish up the rest of this. So I'll see you guys. You're awesome.